the tutorial. Good afternoon, everyone. Welcome to our tutorial on Multiagent CoPilot in Industrial AI Applications. I'm Chaturangi Shalika, a PhD student at Artificial Intelligence Institute at University of South Carolina. And the team, our team is from AI Institute, University of South Carolina, and Bosch Center for AI in Pittsburgh, and Clemson Composite Center at Clemson University. So this is our team, and I'm Chaturangi Shalika, and this is Ranjit Prasad, and Utkarshini Jayamini. So we are from AI Institute, University of South Carolina, and Dr. Corey Henson, he's from Bosch at Pittsburgh, and Fadi Kalash is from Clemson University, and our supervisor is Dr. Amit Sheth. Unfortunately, he couldn't make today at this conference. Yeah, so to begin with, let's start with the first session on introduction and explaining the objectives of this tutorial. So let's begin by understanding the driving forces behind this work. Currently, we are witnessing rapid industrial digitalization. So modern manufacturing field is now flooded with high-frequency sensor data and increasingly complex automation pipelines. With the move toward this Industry 4.0 and 5.0, factories have become more connected, intelligent, and autonomous. However, the traditional autonomous systems in most of the industries haven't kept pace. They are still grounded in fixed logic and hard-coded control rules that don't adapt easily. And also, they fall short on explainability, means they can detect a fault, but they can't explain why it occurred and also how it propagates throughout the systems. So critically, they lack context awareness, means they don't reason across time, processes, or sensor modalities within manufacturing facilities. And also, on top of that, AI adoption in current manufacturing field has been fragmented. Means different tasks like anomaly detection, forecasting, quality control in the manufacturing facilities currently are handled by isolated AI models that don't talk to each other. These systems treat each of these functions in a silo, and they ignore the rich interdependencies that exist in industrial environments. So this brings us to the core gap, which is the lack of integration and interactivity among systems. The siloed AI models can't explain why something went wrong, and also how it impacts the downstream task or what to do next. Also, they don't support reasoning or complex decision making in evolving factory settings. And that is why where the idea of co-pilots comes in. They offer more interactive, explainable, and integrated approach towards modern industrial intelligence.
Okay, so now you know the motivation behind it and why we need copilots. We can uh, jump into the copilots. So copilots are AI system for augmented intelligence. What I meant by augmented intelligence is that there is a human along the way who's interacting with it, with the agent, and is able to interact and infer and make decisions. So it's a human in the loop AI that infer causes, that predicts outcomes and suggests action. So it's not a very reactive, it's not just reactive, it's a interactive sessions. And it explains decision with traceable reasoning. So you know why certain things happen and what is the reasoning behind those things. So, and it's very grounded as well. And it adapts to evolving production goals and system changes. Because it's very interactive, it's able to identify these things and able to get informations in each process, and it's able to adapt to its production goal, and it's able to change accordingly. Now, what is a multi-agent copilot architecture? Multi-agent, as the name suggests, is consisting of multiple agents. Each agent's work may be independently, but they all work come together to produce a cohesive output for whatever task that you have. So the architecture that we have developed is a multi-agent copilot called SmartPilot, which we will define later on. It's a multi-agent copilot for smart manufacturing, and it does several things like anomaly detection, forecast. So all these agents work independently, but it again produces cohesive output for in our case manufacturing, and it collaborate to provide, as I said, cohesive and explainable insight. And it's inspired by human expert teams. That means each agent contribute to holistic situation awareness, so it's able to understand and get information. So the objectives of tutorial is to introduce 4.0 and its challenges. It's explore the roles of Copilot and multi-agent collaboration, learn the foundation of Neurosymbolic AI, gain practical knowledge of Copilot development, discover the importance of causality, and apply learning across domains through demonstration. So let's give a quick overview of what we are going to cover throughout the tutorial. So me and Chatranki was going to start with introduction and objective, where we again we talk about industry 4.0, the need for an advanced AI, and we'll formally we go through a little bit of neurosymbolic AI and why it is a for us a key enabler for copilots. And then we will go through overview of copilots for industry, where we explain copilots custom, compact, and neurosymbolic design, and we introduce multi-agent copilot. All these terms will be defined later. Then we will build copilots for industry with SmartPilot, which is a multi-agent copilot that we have developed for manufacturing. We will demonstrate SmartPilot's agents and their integration with knowledge bases. Then we will move on to incorporating causalities to SmartPilot. So Utkarshni will define causality, what is the importance of causal discovery, effect estimation, and reasoning embedded into SmartPilot. Then Dr. Henson will move on with real-world applications in industry, where he will highlight industrial use cases in using multi-agent copilots. Finally, Fadi will talk about real-world deployment challenges, where he'll discuss integration into legacy system, scalability, and real-time deployment hurdles. All right.
Yeah, moving on to the second main section, the overview of copilots for industry. So to begin with, so earlier in the industries or the manufacturing facilities, they had tools like static dashboards, SCADA interfaces, and rule-based control panels. So these systems were mostly static systems. They served the industries well, but their capabilities were limited. Also, these systems worked in silos. They required manual interpretations, and the output were purely reactive. They did not have the ability to learn, adapt, or reason across various tasks. But in today's complex manufacturing environments, these limitations make it so hard for manufacturing facilities, and it is so hard to respond to dynamic conditions when we are using them, and it is so hard to optimize the system performances as well. So that is why we need a smarter and more integrated approach, so that leads towards the agentic systems. So in contrast to the traditional tools, the agents mark the first step towards the intelligence in industrial systems. What are these agents? So these agents are software entities that can perceive the environment, reason over data, and perform actions, often with some degree of autonomy. For example, in manufacturing, agents might monitor sensors, they can detect anomalies, and or they can trigger alerts based on the anomalies they detected. But the complexity of real world environment but when the complexity of the real world environment grows, and as tasks become more interdependent, uh, a single agent acting alone was not actually enough. So this brings us to the next stage in this manufacturing evolution, which is agentic AI. So, agentic AI refers to systems where multiple intelligent systems, means agents here, work together, coordinating in order to achieve complex goals. So, these systems can decompose complex tasks into simpler tasks and share memory and maintain persistent workflows. Thereby, they enabled the adaptive and collaborative behaviors. For example, in a smart manufacturing setup, one agent might predict anomalies, and then the second agent might analyze the root causes for the anomalies, and another will retrieve the semantic explanations for all these findings. So they all work in sync to support real-time decisions in a manufacturing facility. So compared to the traditional AI that act alone and reactively, this agentic AI concept can enable a goal-driven orchestration across multiple manufacturing-based tasks, and that make it far more powerful in complex and dynamic environments in manufacturing. So to build truly agentic systems, we should rely on core design patterns that can guide agentic behavior. So what are these agentic design patterns? The first one is reflection, where the agent evaluates and improves its own outputs through the iterative feedback loops that he gets from the environment. The next is tool use. The agent enhances its capabilities by invoking external tools, APIs, or databases whenever they are needed. And the third is planning. Planning means the agent breaks down a complex task into smaller subtasks and or else some manageable steps and execute each of them separately. And finally is the multi-agent concept, where multiple agents or subsystems can be built and they can specialize on multiple different subtasks and integrate and coordinate in order to achieve these simpler goals. So these patterns enable the agents to go beyond passive roles and take on more structured and goal-directed behaviors. So these agentic systems fall along two key dimensions. What are they? That is autonomy and control. Autonomy means how independently the agents will operate, and control means how tightly their behavior is supervised. So in this diagram, so in the lower left, we have RPA or the rule-based systems. These systems had very low autonomy and they are very low in flexibility also. So for example, this can include like scripted tools that follow a fixed control rules. And then moving up, we have workflow agents. These workflow agents add more control logic, but still they lack in autonomy. They can orchestrate predefined tasks in structured workflows in facilities. And on the right, we have autonomous agents. They act with high independence, but they had minimal oversight. They were ideal in dynamic and like unpredictable settings. And in the top right, we find semi-autonomous agents. So these agents can balance autonomy with oversight. So that make them ideal for human-in-the-loop environments like the industrial copilots.
Okay, so now you understand the limitations of tools, agents. So these traditional tools are static, like static dashboards, SCADA interface. These operate in silos and they require manual interpretation and is very reactive in nature. So there is no learning, there is no reasoning along with it. So it's very static. So we need something which is interactive. Agents is a little bit better, and it performs tasks autonomously or semi-autonomously, and it can monitor data, trigger alerts, and automate routine actions. And but these also have very limited reasoning. It's not very interactive, and it's very autonomous, and it's often rule based or narrowly trained on single tasks. So thus we require something like Copilot system. So let's formally define what is a Copilot. Copilot are interactive AI assistant that helps human make better, faster decisions. So the key characteristics of a copilots are they are augmented intelligence. That means it's not autonomously working, but there is a human which supports the copilots than fully automating it. It's interactive, human in the loop. So there is always a continuous dialogue with the users. There is you ask some questions, you clarify some questions, and then you suggest some questions. So it's always completely evolving. There is a learning from user and data. It updates preference while we interact. It refines strategies while we interact, and it adapts over time. It's a modular multi-agent design. That means we can have multiple agents which can work independently, but they come together and collaborate with each other and make decisions to whatever system that we are working on. Okay, so in generally there are two major types of copilots. There are task specific copilots and there is like domain general copilots. So let's see what are these two. So task-specific copilots, as the name suggests, are like very designed to assist a very narrow, well-defined or a class of tasks. So it's very constrained to the task that we are working with and in a given system. Their knowledge, reasoning, and capabilities are scoped tightly around that task. So it is very specialized and it's custom towards that task. GitHub Copilot, for example, is a very good example of those kind of task-specific copilots. Domain general copilots are, as the name suggests, again, it's an open-ended dynamic task. Dynamic task across a broader domain by combining multiple competencies together. So it's not task specific, it's very general, and it can coordinate multiple subtasks, and it can have multiple agents work together. Auto GPT, for example, is a domain general copilot. So what's the difference between Copilot and classical AI agents? Classical AI agents, autonomous goal-driven systems that act on behalf of users with very minimal interaction. Copilots, on the other hand, are interactive, assistive-based systems that enhance human-in-the-loop decision-making. So the emphasis on copilots is these three things: collaborative, that means it's collaborate with the human, it's context aware with grounded reasonings, and it's conversational, so there's always interactions. So classical agents replace human decisions, while copilots augment human cognition and judgment. So these are some of more differences. Classical AI agents main goal is autonomously optimize objectives, where copilots it's assist human in decision making. It's fully automated classical agents, whereas copilots are human in the loop systems. Classical agents are more or less one shot or scripted, where copilots are more conversational and contextual. Classical agents requires offline retraining, while copilots are more real time. It happens within the session, and it's memory informed with both long term, short term memories. Classical agents are AI, which AI decides, so it's more autonomous, where in copilots are human validates. Examples of classical agents are self-driving car agents, chatbots, while in copilots it's GitHub copilots that we said before, or Auto GPT or MS365 copilot, etc. So when we define the architecture of a copilot, there is like 5 major things. One is a perception module where the copilot take in the data. The data can be multimodal. It can be sensor data, time series data, or images, videos, textual data, etc. So these perception modules are copilot sensors, which is responsible for pursuing the environment through the raw input data. And the next one is the knowledge modules, where this is Copilot's long-term memory, where it's stored this grounded knowledge through structured informations like ontologies or knowledge graph, which we're gonna talk about later. Then there is this short-term memories, where Copilot remembers the short-term things and it's able to update its session through these short-term memories. And this is used for much more for personalization and evolving assistance. Then there is a reasoning engine. This is where Copilot thinks. It's able to take in a question and it's able to understand this question and updates the interaction accordingly. So it processes inputs, it draws inferences, it simulates some decisions and discover like causal links, why certain things happens and so on. Then finally, there is an interaction interface. This is how the Copilot communicate with the user. There is probably through a web interface, and it interprets questions and it's able to take it from all the agents together, and it's able to answer questions from users in a single interface. And it also asks clarifications. So you can ask it through this interaction interface.
Yeah, now you know how agentic systems and the difference between tools, agents, and copilots. So, and as Ranjit described, we saw that the agents have been integrated with external these components, and then the copilot systems were emerged. And these copilot systems augment the capabilities of the agentic systems through more advanced natural language interactions, and they gave like proactive suggestions to the problems that we have in our hand. So these copilot systems are actually guided by four key design principles. So these design principles make the copilot system effective and more trustworthy in industrial environments. So let's see what are these components. So the first one is the modularity, means the system is built from interchangeable components like reasoning engines, perception modules, and memory components. So this allows the Copilot systems to be more flexible, scalable, and it allows for easy maintenance as well. And second, we use hybrid symbolic neural integration. So the neural models include components like LLMs, statistical models, or any deep learning or machine learning models. They offer more adaptability to the systems. And while symbolic reasoning methods like logic systems or causal graphs or ontologies and knowledge graphs, this can add more structure and interpretability to the Copilot systems. The third one is domain grounding. Uh, so these Copilot systems aren't generic systems. They can embed domain-specific knowledge that we can get from sources like sensor specifications, if it is the manufacturing or industrial settings, and like robot behaviors, or there can be certain anomaly types in the manufacturing facilities. So these are domain-specific knowledge that we can use in industrial-based copilots. So we can use sources like structured sources like external databases or ontologies or knowledge graphs to gather these external domain-specific knowledge. And finally, the human in the loop oversight. This design principle ensures that the copilots remain interactive and transparent with the users. So the users can ask questions, correct or guide the system behaviors when needed. So together, these design principles make the copilots not just intelligent, but they enable usable, reliable, and context-aware adaptation of manufacturing behaviors. So these industrial copilots should be designed with several critical properties that make them usable for real-world deployment. So what are these key properties that we need to take care of? The first one is they offer context-aware assistance. Means that it can understand not just the data, but the user's current task, system state, and the environment also. So this ensures that the support they provide is always relevant to the context and the environment which the manufacturing operations are going on. And secondly, they come with user interactive interfaces, from chat-based tools to visual dashboards. So these interactive interfaces allow the operators to ask questions, get explanations, and stay in the loop. And thirdly, they ensure seamless integration with the existing manufacturing tools. Whether it's engineering or automation platforms, copilots can fit into familiar workflows and they can enhance them, often with natural language capabilities. Importantly, copilots handle task automation with human oversight. They take over routine or complex manufacturing or industrial tasks, but they always leave the control in the hands of the user. And they also bring domain-aware multimodal intelligence, means that they can combine structured sources like ontologies or external knowledge graphs and external structured data sources with unstructured inputs like raw sensor streams, images, or technical manuals. So this can enable deep grounded reasoning across a wide range of industrial inputs. And finally, uh, these copilots can support continuous learning and adaptation across multiple tasks in a facility. So they can enable personalize the behavior over time in order to match the user preferences and the adaptive and dynamic factory conditions. So what are the industrial use cases that we can develop copilots for? So there are like multiple examples that we can see, like predictive maintenance, anomaly prediction, quality assurance, process optimization, and most importantly, the human in the loop supervision. So Dr. Corey Henson will explain more on these use cases by explaining on the Bosch use cases. So we will not explain that much in this section. So this Siemens CoPilot is a popular and first most implemented CoPilot within manufacturing systems. So this Siemens CoPilot is an interactive CoPilot where it enabled multiple visualization and documentation capabilities, and it was able to integrate seamlessly with the existing systems at Siemens, and it was very good in generating code, and it supported a multiple range of engineering assistance. And also, whenever a new skill needed to be developed, like assembling unknown object, a new object that was detected. So this Siemens Copilot was able to develop the new skill from scratch, and so it was very good in empowering the skills. And overall, it was able to increase the overall productivity at Siemens. Yeah, now let's go to the third section.
Okay, till now we have defined what is a copilot. We've understood the limitations currently of tools and these agents. So let's now go to the SmartPilot. But before that, maybe we can stop for questions if there is.
So it's more question about the presentation. Is there a way we can access this presentation so we can refer to it?
Yeah, it is available online. It should be.
Okay.
Yeah, if you go to the Woha app, there is a link, and in that link, the presentation is available.
Okay. Yeah, I should be able to. Thank you.
Okay. If there is no more questions, we'll just move on to the next session. So now we are going to talk about SmartPilot, which is what we developed, which is a copilot for manufacturing that we have. And so let's formally define. So SmartPilot is an agent-based copilot for intelligent manufacturing supported by a custom, compact, and neurosymbolic AI model. So what are these terms? Custom is it's task specific. It's specialized to perform the certain task. In our case, it's manufacturing. So there is certain tasks for manufacturing that we tackle upon, and those are the tasks that we are solving through SmartPilot. Compact, it is very real time and lightweight, so that we can put it in a edge device. It's not using large language models. It doesn't need billions of parameters, and it's not doing that. And then neurosymbolic, Chatranki has defined a little bit before, but let me refresh the memory. So it contains both neural and symbolic things. Neural as in models like deep learning models, and symbolic as in symbol like structured knowledge sources like a knowledge graph or ontology or structured knowledge sources, anything. And it has causal and common sense reasoning, and it is very transparent and context aware, like we said before on copilots. And it's so these are some of the resources for SmartPilots. So if you click on the URL, you can go, or the QR code, you can go to the paper, demonstration video, and source code. So the paper was put in IEEE CAI last week, and that won best paper. So that's that. And then there is a we have like a demo which is also available in which we are doing in 2 days. So if you are around, please check out in the AAMAS tutorial. AAMAS. Okay, so let's define what are the agents in SmartPilot. So there are basically four major agents in SmartPilot. The four agents are PredictX, Causal Lens, Foresight, and InfoGuide. So PredictX does prediction of anomalies ahead of its time. Foresight does forecast the product's analytics ahead of its time. Causal Lens is for root cause analysis and causal discovery. And then finally, we have InfoGuide, which serves as Q&A chatbots for domain-specific queries and generates some responses. So these all agents interact with each other. And so there is an interaction between agents like PredictX, InfoGuide, Foresight, everything. And there is causal relationship which happens between each other through Causal Lens. And the end users are typically manufacturing specialists, shop floor operators, practitioners working in industrial AI. So they have some knowledge about what is happening. And these are the end users for SmartPilot. So we are gonna do talk about the architecture of each of these agents, but let's show the architecture of the entire system. So there is so many things happening, but what I would like you to focus on is the fact that it's a composite AI system. What I meant by that is that it's a framework that includes technical components such as input teach agents and agent interaction. So there is so many things. So there is like data which is coming through multimodal. So there is time series data, there is images, there is textual data, and so on. And then there is structured knowledge sources like ontologies or knowledge graph and other structured knowledge sources. There is agents which are out there like agent 1, agent 2, agent 3, agent 4. And these agents are interacting with each other. And then the agent 3, which is the InfoGuide agent, produces results in a Q&A chatbot format. So these agents interact with each other, and we get the output in one single agent, and that's how we respond and interact with each other with the agents. So we for this tutorial we will use the dataset from Future Factories Future Factory is a lab in University of South Carolina. And the dataset that we are going to talk about is from that lab and consists of both time series and image data. So it's a multimodal dataset. Time series dataset consists of like sensor data or like pressure, things like the pressure, temperature, things like that. And images, as in from the lab, we have two cameras attached to the opposite corners, and we take pictures. And so there's the image dataset. So these are the two multimodal dataset that we have, and what we currently going to show in the SmartPilot, but it can be extended to any dataset that you can have. So the dataset, so the Future Factories dataset is for a toy rocket manufacturing dataset. So the toy rocket consists of essentially 4 parts. So there is a rocket base, then rocket body 1, rocket body 2, and NOSCON. So we define anomalies as missing of some part of the rocket. So for example, if NOSCON is missing, it is NOSCON anomaly. If rocket body 2 and NOSCON is missing, then rocket body 2, NOSCON missing, and so on. So these are the anomalies that we have. And these, I don't know if you can see the lab setup. So the lab setup is like a circular thing where there is multiple robots is there, and it takes in a part of the rocket and then puts together. So during one cycle, it completes one rocket. So the one cycle consists of, consists of 21 distinct cycle states. So these states are important because each states does something. So for example, state 4 has body part 1 assembled, state 6 has body part 2 assembled, and so on. So there is some, we get some information from each of these states. So the data sets that I said before is from the University of South Carolina. We have another data set called Vegemite yeast evaporation data set. This data set we got from an Australian university, and it is basically the production of Vegemite jam. It is a jam production data set. So there is so many steps happening, as you can see in the diagram. But then it's a production data set, and we use it for production and analysis, like production ahead of its time. The second agent that I discussed before, so this uses this data set. So when we are showing the demo, this is what we are going to show. So the knowledge sources that we have is both, we have structured knowledge sources, and we also have ontology for this future factories data set, and we also have knowledge graph.
Yeah, so in our lab, so we have designed and developed our own knowledge graphs and ontologies for this particular dataset, which Ranjit was explaining, the future factories multimodal dataset. So we have developed a smart manufacturing knowledge graph using this particular dataset and the factory involved in. So what this manufacturing knowledge graph include? It includes all the objects that can be included in the manufacturing facility. For example, like robots, the conveyor belts, and the types of sensors involved, and things like that. And also like more external information about these machines, robots, and the sensors, like the normal operating conditions of these sensors, and the angles of the robots, and what these robots are performing, and at which stage the robot picks the separate rocket components and attach into the current existing product. And also this smart manufacturing knowledge graph stores the relationship in between these all these components. So it's kind of like a huge graph which pictorially visualize the all the relations and what is happening in this production line. And also we have the dynamic process ontology that we developed for this particular use case. So the difference between this is the dynamic process ontology stores the workflows that is in this particular facility. So Ranjit explained that this particular use case has 21 different cycle states. So this dynamic process ontology starts from the first state into the to the 21st state, and then it pictorially shows what are the robots involved, and what is the cycle number, and what sensors involved, what are these sensors performing, things like that. So there are some overlapping content also, but basically this process ontology shows the workflows which is happening in this particular rocket assembly use case. And so, yeah, so Ranjit explained we have 4 different agents. So now I'm going to explain each of these 4 agents separately, and the architectures of them, and more technical details of these 4 agents. So this is the architecture of the predict text agent, which is doing the anomaly prediction. So it looks so complex. So, but I will just explain you briefly what is it includes and what is it doing. So in PredictX agent, we rely on time series sensor data and image data. So these are our inputs. So we got them from the Future Factories multimodal dataset, which Ranjit explained. And then our task is to predict the next time series values, and say if the value is an anomalous value or not. And if it is an anomalous value, we predict the type of the anomaly also. So it's like a 2D prediction. So what are the technical components that we use? So we employ something called decision level fusion approach. So what is this decision level fusion approach is doing is that we have two modalities. So it is multimodal. So we need two different classifiers or different algorithms to process these two modalities. For time series, we used an autoencoder based approach, and for images, we used a pre-trained efficient net architecture. And then we combine this, the results of these two algorithms or these two models into a common representation approach, and then we use a classification we developed a fusion model that includes a feed forward network that represents the output of these two modalities, and then we predict the next time series, and then which is again followed by a classification layer which determines the anomaly type. So the upper part of this architecture shows the time series and the image, how we combine the time series and images, and whereas the lower part shows how we process the image data set and goes towards that. So one important thing is, so we have 21 cycle states in our assembly pipeline, but only in two cycle states we can visually and clearly see the components of this rocket. So we filtered those two cycle states, which is cycle state 4 and 9, and then we continue to our object detection approaches, and then combine it with the the time series inputs. And also here we employ the process ontology that I explained earlier. So we use external knowledge from included in this process ontologies. For example, information like the normal sensor ranges of the sensors in this manufacturing facility. So we infuse those knowledge in the middle of the training process. So we call this a knowledge infused learning approach. So what is this knowledge infused learning? So it is a type of neurosymbolic AI approach. Neurosymbolic AI means we combine neural methods with symbolic approaches. So the neural method that we use is using the autoencoder approaches, efficient net architectures, and the fusion model. And the symbolic approach here is the use of the process ontology. And then the second agent is the foresight agent, which is doing which is forecasting the next hour production outputs. So here we employ just like a simple LSTM approach, and then we also use a knowledge infusion approach here also, where we infuse additional features that are included in external structured knowledge sources. So these external features include information like production metrics, machine data, and downtime data, things like that. So the input here is, so Ranjit explained the overall data set. Here we rely on three products and the weight of the yeast material, which is input in the Vegemite production process, and then we output the next hour the weight of the next hour demand. And then thirdly, the InfoGuide agent. So InfoGuide agent is the question and answer chatbot that we have developed. So this is kind of the main interface of our system. So once you access the SmartPilot, you first interact with the InfoGuide agent, which is the Q&A agent. So if the user query, so it's like a ChatGPT-like interface. So if the user query relates to these different four tasks, then the InfoGuide agent is able to classify the intent of the particular query and then direct it to the respective agent which needs to be invoked. So for example, if the user query has context related to anomalies, it will invoke the predictive agent and give the prediction accordingly. And then if the query led to causality, and then it invokes the causality agent, and same for the foresight. And for the other types of questions, it invokes the reasoning engine that is inside the InfoGuide agent itself. So this InfoGuide agent is rely on the manufacturing manuals that we got from mainly from the Future Factories dataset. So these manufacturing manuals include data like manuals related to robots, sensors, and operating conditions. So we have developed a internal database which includes the summarized information from these manufacturing manuals. So this summarized uh, PDF is the internal database that I was referring to. And then when a user asks a question, if it need to get the information from this summarized PDF database, then we use the retrieval augmented generation approach, and then we follow some similarity measuring techniques to check the relevance of the particular answer and the question. And then if the answer is in this context, then we polish the answer using a mixture language model, and then we give the response to the user. And then so we will explain the causal lens agent in the next part, because Utkarshini is explaining the causality section in the next section. And then now let's see how we have incorporated the agentic AI principles in our SmartPilot. So as I explained in the previous section, agentic AI should have three sections like understanding, content generations, and taking actions. So we use pre-trained language models. We use Grok API to access the pre-trained language models. And also we use semantic embeddings to understand the user queries and the context. And here we use semantic embeddings to match the questions into a common space, and then give the relevant answer to the user. And then we do content generation, means we dynamically generate the counterfactual causal explanations, and we analyze the feature metadata and enrich the natural language answers from the knowledge sources that we have, the ontology and the smart manufacturing knowledge graph. And then in the third section, when taking actions, so SmartPilot is able to generate codes related to causal discovery and root cause analysis, and also it can handle intervention queries also, and we can trigger our root cause analysis automatically after the anomaly prediction is done, and things like that. So we have achieved almost fully in understanding and agentic content generation sections, while we have done most of the sections in the action part as well. And then let's see which type of agentic system our SmartPilot falls on. So SmartPilot is a human-guided and semi-autonomic agentic system. So when we are doing the demo, you can see how it works and how it performs with the user queries. And then let's see how we have used design patterns and CoPilot design principles in SmartPilots. So first, talking about the design principles. So these design principles are the architectural guidelines that we have used. So I explained four principles. So the first principle, modularity. So SmartPilot implementation is that the system can break the complex task into loosely coupled agents and tools. For example, we have separate agents doing forecasting, anomaly detection, causal inference, and like semantic matching, like ontology question and answering. And using this, we have been able to support rapid extension, debugging, and agent level reasoning, things like that. And then we use sources like ontologies and knowledge graphs for domain grounding purposes, which we have been able to map the AI outputs into real world variables like robots, sensors, anomalies, things like that. So this has been able to improve the alignment approach in our system with manufacturing context, and it is able to enhance the trust with the user and the system. And then we use a hybrid symbolic a neural approach. So means that we use techniques like deep learning approaches that we explained in the predictex and the foresight agents, and we integrate these agents with causal graphs, rules, and ontologies with LLMs, transformers, and similarity models, things like that. And this allows more explainable and adaptive responses towards the user. And then fourthly, human in the loop concept. Uh, we can enable natural language queries, causal overrides, and graph editing by the user. So these are all the things that are available in our SmartPilot. So this has been able to give more transparent and more reasoning support towards the inputs provided by the system. And then talking about the design patterns, so here, actually, modularity means the agent allows dynamic graph editing and re-evaluating its outputs. All the things are guided by human refinement. And then we use tools like external causal discovery methods like Lingam and Defun, and also uh, like uh, knowledge sources that I explained. And then planning means SmartPilot enables multi-step workflows. Means we first upload our dataset and we can go to anomaly prediction and followed by causal discovery, counterfactual evaluation, and RCS. So there is a defined planning that we have incorporated in SmartPilot. So all this planning is domain grounded, and these are the planning steps which are mostly included and needed for existing industrial environments. And then multi-agent means we have separate agents doing separate tasks, and they handle distinct reasoning capabilities and data modalities.
Okay, so we will now go on to the demo of SmartPilot. So the premise of the demo is that you are a new manufacturing employee which comes into a company, and so you know something about the manufacturing, but you are still unaware of the environment that you are in. So you want to know more about the machines and things like that, and you will come across several problems and how we are going to solve all these issues. So that's what we are going to talk about when we look into the demo. So there are some strange values that occurs. There is anomalies occur. So how are you going to deal with it? So there, how can I achieve certain target? How can I achieve certain production goals? So how are we going to do all these things, and how to operate this machine? Certain machines, you don't know what the machine is about. How are we going to know about certain characteristics of machines and so on. So these are the premise that we are going to work with. So let's go to the demo. Okay, so while we are setting up, if there is any question specific to the SmartPilot that we have discussed, please feel free to ask and we'll be happy to answer.
Yeah, so this is a free online link that if you want to access our system, you can use this particular link and access, and it's available online if you want to access. And maybe I can give a QR code also. Yes. It's fine. Can I share?
Maybe stop sharing and
No. Yeah, this is the QR code if you want to access the site now. Yeah, so now let's see how SmartPilot is working. So this is our SmartPilot, the agent-based copilot for intelligent manufacturing. And when you are logging to the system, you will see this window. And so here in the left panel, we have some sample questions that you can try. So imagine that you are a technician working in a manufacturing shop floor, and so I'm trying to figure out what the insights of my sensor readings can tell me. So I'm a new hire in this company. So I see there are some unusual sensor patterns in robot 2 and 2, 3, and 4. So maybe I know about this, or my supervisor is saying me that there is something called the SmartPilot CoPilot. So maybe I can use the predict text agent to figure out if there is an anomaly going on this time step in these separate sensor readings and the robots. Maybe I can use the predict text agent and answer questions. So I'm asking what is the anomaly status when the current sensor values for IRO2 gripper potentiometer, IRO3 gripper potentiometer is these values. So these are the sensor values that is existing. So before that, actually, we have to upload the data set here. So So I will take a sample of the real-time sensor dataset and I will upload here. So it will give me a dataset, an overview of the dataset with the number of rows and the columns involved. And it will also give descriptive statistics of the dataset for all the sensor values. So now I have, since I'm a new hire, I get a complete overview of the manufacturing setup and what kind of sensors it includes, the data types it has, and overall statistics of this data set. So let's ask the question to check if there is an anomaly or not. And I picked three variables in this particular data set: IRO2 gripper potentiometer, 3 gripper potentiometer, and 4 gripper potentiometer. So all these are like the sensors attached to the robots that we have in our manufacturing facility. And then yeah, it gave me that there is an anomaly, and like, and also it invoked the causal agent also, and it produces the causes for the root causes for this particular anomaly. And then maybe I want to know some more information on this particular pipeline. So I asked that give an overview of the toy rocket manufacturing pipeline. Yeah, it gave me an answer of the types of sensors involved and the tolerance ranges of all these sensors also. So here actually these tolerance ranges we get from the process ontology and the knowledge graphs that we have developed. So here you see the interface of the InfoGuide agent, and it is interacting with the other agents for predict text and causal also, and giving these inputs, giving these outputs. So this is how the predict text is working. And then let's say that so I am a new hire that I joined this week. So my supervisor is saying me to achieve some target in the production lines within next 3 days. So for this, I want to know how to allocate my resources efficiently in a schedule in order to for me to achieve this target within the next 2 3 days. So uh, I want to know how can I effectively achieve this target and allocate the resources accordingly. So I want to know how the the production is varied and how much my facility will produce the productions in the next hour. So I'm asking what is the next hour's production line in the Vegemite production line when the current values are 1090 and 1480. So these are all the weights of the production, the yeast that is involved in this facility. And then it gave me product-wise weight of the yeast production involved. And then say that I want to know more information on this module that is used by this particular pipeline. And then it gave me the how we have created the model and the parameters and data, things like that. Say that I want to know more information about this data uh, to achieve, to allocate my resources and how it can aid my decision making. And then it gave me more information on the historical data that this particular pipeline includes. And then if I want to know about features that can be used to uh, predict this Vegemite, then it retrieves this information as well. Okay, so this is how the foresight agent is working and how it is interacting with the InfoGuide agent to give the a particular output. And then so this is my first week in this company. So I don't know how to operate these particular machines and what are the sensor ranges, and I am confused, like I don't know which manual to refer, whom to contact, and things like that. So uh, maybe I can use the SmartPilot uh, to clarify my questions. So I'm asking what are the types of sensors in this manufacturing line, and it gave me a whole bunch of details that includes the separate sensors and the functions and also the specification of this particular sensors. So this all answers we got from the process ontology that we have designed and that this particular smart pilot is connected to. And then maybe I can use this to learn more about what types of anomalies in this particular pipeline. And then it retrieves the answer from the knowledge graph and it gave these 3 types of anomalies. Maybe I can ask more questions like what are the types of anomalies related to this particular load cell or the particular sensor values that you see in the first stage where we upload the dataset. And then it gave me the types of anomalies associated with this, the sensor that I input here. And then maybe I want to know how many robots are in this setup so that I can get a sense on how should I allocate which task to which robots and things like that. And it gave me that there are 4 robots in this setup. So all these values are inferred from the sensor data, the time series sensor data sets, which I input earlier. And maybe I want to know more about what types of sensors connected to robot 3. And it gave me the types of sensors associated with robot 3. So all these are retrieved from the knowledge graph that we have developed. And I want to know what is the manufacturer of the particular sensor. And yeah, it retrieved the information, and it is good in inferencing these things as well. And it like if I want to ask about the tolerance ranges, and it gives me the tolerance range including the type of the measurement as well. And also, so these tolerance limits and the ranges are kind of, so these are some similar questions. So it is very good in identifying the similarity in between the questions and giving the correct response as well. And like we can ask the same question in different ways, and it infers the correct answer and gives us the response. And so I'm asking the description of the sensors. It gives me the description along with the measure, what is this sensor doing, and the specification of these sensors. And also it is very good in tracing the path in between the separate elements and the robots and the functions involved, things like that. Yeah, so this is the demo that we have for the first 3 agents. And yeah, if you Yeah, so this one robot has different sensors, and this robot 3 has IRO3 gripper and that IRO3 gripper potentiometer is a type of potentiometer sensor, and potentiometer sensor is attached to the gripper of the particular robot, and so it is good in, it can trace the path from robot to the actual grounded sensor values.
You can show some normal, there is no anomaly.
Yeah, maybe. Yeah, so this is a state where we can find there is no anomaly in this particular values. And if there is no anomaly, then we don't call the causal agent to do root cause analysis, and it can infer, like it can understand that no further analysis is needed and gives the response accordingly. Yeah, and in the next section, actually, we will demonstrate how the causal agent is working after Utkarshini explained about the how to incorporate the causality into CoPilot systems. And so you can access this particular QR code and play with the SmartPilot. And if you have any questions, reach to us, and we value your inputs and suggestions.
Is to like let's say I have another data set, another time series data set. Are there any pre-processing steps involved in using the SmartPilot? So currently you are using 2 separate data sets, and if I want to upload my time series data set.
Yeah, so it is pretty easy. Like you can upload any a time series dataset from here and access with all the functionalities. So currently we have trained the models and the knowledge base for the for the future factories dataset that we have in our university. But if you have a facility like that, and if you have manuals related to this particular facility on the robots sensors associated, then you can obviously use our internal knowledge base and access through our data processing pipeline and get the processed information from these manuals and put it here and access with the info guide agent. And then if you have a model a time series model that you have developed for anomaly prediction or forecasting, then you just have to change the path here in our code base and use the particular call the particular model and give your values and take the input. So it's pretty scalable. And also the smart manufacturing knowledge graph that we have developed. So we have used general standard design patterns and sensor specifications. So most of the manufacturing industries in this world obey these concepts like SOSA concepts and other semantic web concepts. So that particular knowledge graph includes all the sensors and uh, the the robot types involved. So it is, so you just have to call that through particular querying languages and you can use it. And if you have external knowledge sources like process ontologies, you can use it. It's pretty scalable to use to your needs. Yeah, if nobody has questions, then.
So I think since we do have some bit of extra time, it might be great to talk a bit more about the context of why this is so impactful. And I believe the best way to kind of go on about that is to maybe we can go back through the data set and give a bit more context over what's happening and how this smart pilot was able to really utilize this data set and help us kind of understand what are these responses really indicating for us. So I know throughout this presentation, we kind of went through it really quickly to kind of so we can go through all the topics that we want. But given that we still do have a couple of minutes, I think it would be very beneficial for this tutorial to kind of go through and have some more details. That way, whenever you guys access the website itself and try to talk with the Copilot and see these responses, you can understand what it's really trying to tell you and what it's saying. So as Ranjit had kind of talked about before, one of the data sets that they utilized was the Future Factories data set. And this is a data set that was created at the McNair Aerospace Research Center down at the University of South Carolina. And the data set was created from a manufacturing system that is fully deployed and operational. And essentially what the system does is it assembles and then disassembles a 4-part rocket that which can help us imitate what a assembly system in a real manufacturing facility might look like. So essentially, in this manufacturing system, we have 4 robots that operate together. It begins from well, this picture is a bit small, but we'll try to use it as best as we can. It begins with one robot that handles a tray, takes it from a material handling station and puts it on a conveyor system. This conveyor system is used to transport the rocket from one location to another so that the other robots in our assembly system can then use it, assemble what they need, and then return it back into the transportation system. After the first robot places it on the conveyor, the conveyor will move it around, and then we have 2 different robots that work together collaboratively to put together the 4 parts in their own separate assembly stations, and then return that fully assembled rocket back to the output of the system. And that's essentially how we were able to develop this whole assembly cycle. Now, we also talked about the idea of a cycle state. And these cycle states play a very huge role in the creation of our process ontology, which we'll also talk about in a couple of minutes. But essentially, these cycle states allow us to understand where we are in our assembly system. Are we still at the point where the robot is placing the tray on the conveyor? Or are we at a point where our 2 robots are working together? These are very essential signals for us to know because it helps give us context to the data that we are receiving. We do have 21 cycle states, and in these 21 cycle states, it outlines bit by bit what each part of the system is what is happening in each part of the system itself. And throughout the system, we have a lot of different sensors. we have on each robot, we do have two sensors that are mounted on the end effector of the robot. These sensors allow us to know, is the gripper of our robot closed? Is there something in our gripper? This helps us to understand better as well what is happening in our system in that specific cycle state. And so since there are these two sensors on each robot, we end up having about 8 of those sensors employed within the system. And those sensors are called a potentiometer and a load cell. Those are two words that you'll probably see a lot if you're interacting with our SmartPilot. And you probably also saw it in Chatterley's demo. So essentially, the potentiometer is the sensor that lets us know if the gripper is open or closed. And the load cell is a sensor that lets us know if there is a part inside of my robot. Because say my gripper is closed, that doesn't really tell me if there's something in there or not. Maybe the robot went and picked up the air. I don't know what happened. So the load cell lets us know there's actually something inside of the gripper. And that also helps us with the idea of the anomaly detection. Well, say I want to know, well, my final product ended up missing a nose cone. Well, when did it miss that nose cone? I'm not really sure. So now let me look through my data. I look through my data and I see, oh, this robot closed its gripper, but it didn't actually hold anything. That's why my final product didn't really have a nose cone. So this data set, if anyone is interested, is actually available online as well. So it is available on Kaggle, and because it is such a large data set, we have had to kind of distribute it across multiple links. But within this data set, we do have a paper which describes everything that you would want and understand what's in there. We do have analog signals, and we also have images within our data set. So this is the actual system that I was talking about, where you have the robots all work together and the conveyor itself. And then within the actual data set, we have a lot of process signals. So there's a whole table over here. A lot of process signals that tells you what's happening, what is on, what's operational, what are our sensors telling us, and then also what configuration our robots are in. And then and then there are also images. This is actually a very novel idea when it comes to manufacturing data sets, which is the integration of both images and analog signals together. And it has done great strides in helping to improve the utilization of AI in manufacturing systems, because sometimes analog signals by themselves are not enough. Images, in addition to images, we can derive so much more context and so much more insights about our manufacturing system. So we do have a bunch of images that have also been taken throughout this data set. And this data set is quite a large one for manufacturing systems. It's about 30 hours of operation. So our team actually were monitoring our system for 30 hours while it's working consecutively, so that we can collect that data and do some very fun and great research from it. And yeah, so essentially you can find this data set on Kaggle, download it in multiple through the multiple links on it, and all the different information that you might need to be able to use it as well is all present in this paper. Since we do have a data set that is only analog, if anyone is interested in that, and we have a data set that is also multimodal. The analog data set has higher frequency than the multimodal one. So if someone is interested in a more real-time and more with a higher resolution data, then the analog data set's for you. If anyone wants to use cameras, then the multimodal, I think, would be a great way for you to get introduced to it. Okay. Since one other demonstration that we can also show you to kind of help give some more context about how the process ontology that was used in this CoPilot and this data set can both be combined together is the idea of explainable AI. So let me try to pull up a video real quick. So let's say I am again a technician on the shop floor, and suddenly, we had this anomaly that occurred with our product. We have this defect where we ended up with without a nose on our four-piece rocket. Well, I want to know why that happened, and I also do as a technician, I would love to have a machine learning model, for example, that can first classify to me, oh, your final product has this defect. Well, okay, why do you say it has this defects? Like, why do you think it happened? This is where this process ontology can come in. The process ontology, as was also explained by my colleagues, essentially is a knowledge graph that walks us step by step about what the process looks like in our manufacturing system. So if you remember, I talked about the 21 cycle states that we have in our manufacturing system. We have some cycle state 1, where the robot first puts it on the conveyor, all the way to cycle state 21, where the final assembled rocket gets returned. Well, we were able to map out these 21 cycle states into a knowledge graph. And in each cycle state, we can actually define what happens in that specific time frame, map out what equipment is operational through that time frame, and then what does a normal operation look like throughout in that specific state. In this specific demonstration, this sort of pipeline where we go from a time series classification model telling us, oh, I'll be talking over this video, don't worry, so we don't really need a noise for it. We don't need the sound for it. It'll basically go from telling us from, oh, my classification model told me that I'm missing this part. And then after that classification is done, we can sort of figure out why it has decided this, why it was able to predict that. This is a quick demonstration of how the rocket is actually assembled. So those two robots were able to work together to assemble our rocket, and then finally, this fourth robot actually disassembles it again, so that it goes back as an input to the beginning of the system, and we have this sort of circular path where our system can keep going, and we keep collecting data. But now look at this. What's going on? There's no notes going here for some reason. I don't know why. Well, this is what this demonstration is all about. It'll be able to tell us why we were able to classify that there is no scone. Essentially, what happens is once our system is working, we'll just be collecting the time series data all throughout. So I'm just gonna skip through here a bit, all the way until we finally assemble our rocket. And as you can see, we have a very also intuitive user interface on top of our CoPilot and everything. We love our interfaces. We love to make our technicians' lives easier and our engineers' lives easier. So essentially, we take all these cycle states, we take all the data, you can see it right there, and then finally we are able to classify based off of this data, and it tells me that there is, in this case, we actually have a top body and no nose cone, so that's even worse. And I really don't know why that happened. So now what we're going to do is we're actually going to take this time series data that we collected, and we're going to run it through our process ontology. And this will actually help us to come up with some user level explanations about why these issues might have happened. And this is a quick screenshot of how this ontology looks like. You go from say 1 to 2 to 3 to 4, and each one, what robot is in operation and what elements each robot has. And within each element, you do also have some specific function elements, like what is the roamer operational range for these sensors, what is the temperature they should be at, and so on. And based off of that, we kind of iterate through all the time series data. And this is just giving us some more information about what's in our ontology itself. I'll skip through here. And this is how the final ontology looked like. And now, say I want to see why my classification model told me that. So it's going to iterate through my time series data, and then boom, we got some results here. Well, okay, now I see why we might be having some issues. Robot 2 was not able to pick the body 2 from the conveyor. And our processing knowledge was able to tell us that because it was able to look at the robot 2 gripper potentiometer, remember one of the sensors that we talked about earlier. So I looked at that potentiometer and it saw that the values within our potentiometer for this cycle state seem to be anomalous. And so it can tell us that this might be one of the reasons that we are having this final defect in our product. And then so on for the other ones. Look, we have a robot 2 potentiometer again here, but this time in cycle state 7. So you can see that the error kind of propagates throughout our process. If we have an issue in the first cycle, then that issue is going to continue later on in our process, and then so on. Robot 3 and robot 2 again. So here you can maybe tell our technician, maybe you should go check out what's happening with robot 2. Why isn't it really picking up the part? And so then they can do that, and we can continue on with our lives and hopefully be able to come up with some better quality products. And I think with that, we can break for the, all right, you have 30 minutes? Okay, so yeah, I guess then now we have about 30 minutes of break. Hopefully that wasn't too much information thrown at you guys in the last couple of minutes, but if you have any questions, I'm happy to answer them. And yeah, thank you so much.
I think we will start. Okay, so on to our fourth session. You guys learned about what are copilots, how copilots are helpful in the agentic framework, the design patterns, and some of the use cases of our smart copilot in terms of prediction, forecasting, and the info guide agent. Now let's look into, is there even a need for causality in copilot? And if there is, why do we need causality in this smart copilot setup that we have seen so far? So we all know that we have seen there has been agents developed for like booking travel, booking tickets. Travel agents are one of the most common agentic framework that we have widely seen recently. And it's also easy to make have like automated agents do some automated tasks. So for example, agent could help us summarize our Zoom meetings. So there is an agent which is working in the background and summarizing or creating meeting notes for us. So they are very good in some of these automation tasks. They're good in following instructions in case. But are they actually capable of independently setting up their goals or adapting to a new environment or maybe thinking on their own? So let's say you developed a copilot or you developed an agent for Zoom. Now, how easy it is to transfer that same agent to a team setup, for example, or if let's say something changed in our Zoom setup, how easy is for these agents to quickly adapt to this new environment? It is only possible if they understand the underlying framework or underlying model of the environment they are in. Or let's say if we want to deploy them in the real world scenario, they need to understand what our world or what our environment consists of and the relationship between the environments and the variables that we see there. And I really like this quote by Dr. Yuda Pearl, where he says that if we really want to build intelligent machines or intelligent agents, we have to teach them the cause and effect. So we as humans know that, for example, let's say if I start the session 10 minutes late, we're going to end up, that will cause us to have a later ending. So we have that understanding, but most of these AI systems or agents do not have the causal and effect analysis or modeling of this world. Another quote which I really like, you have heard these quotes that we have already achieved AGI, artificial general intelligence is already here, but we keep on hitting a roadblock or hitting the wall when we are trying to develop systems which can actually achieve AGI capabilities. In practicality, we don't see those transformed from theory to practical. If we actually want to do that, we need three fundamental representation in our AI system: space, time, and causality. There has been significant amount of work already done in representing space and time in AI systems, but causality is still an open-ended research, which significant work has been done in recent few years. And in short term, what will help us, so enabling representation of causality in AI, it will make it easy for us to explain why a machine learning model is delivering a particular result. And in the long term, maybe we would have an AGI level of understanding in our systems. So let me give you a quick primer about causality. So Dr. Yuda Pearl, he has developed this ladder of causation, where there are 3 rungs on this ladder of causation: seeing, doing, and imagining. The bottommost rung of ladder of causation, which is the seeing part, is what we typically do in our current machine learning models or AI systems, where we observe and we see, what if I see this, what would have happened? So what is a load sensor value? So you saw the demo in the previous sessions, so that we had gripper potential, we had a load sensor, potentiometer. So let's say, what does a load sensor value of 1400 tell me about an anomaly? So in this case, we are just observing the system that we have. And that's where our current machine learning models or AI systems are, which are mostly correlational based or association based on the observation data. And graphically, if you want to represent this information, it is represented as a Bayesian network, where we have additional information about, in this particular edge or this particular path, what role a node plays. So a node can play 3 types of roles. Either it could be a treatment node, which is the first initial node, or it could be an outcome. So this is the final event that has occurred, or final variable that has occurred, or it could be a mediatory node. So in this path, it could be, let's assume that this arrow goes from A to B, and let's call it C. So in this case, the B node would be the mediator node, or in the sequential analysis. Moving up the ladder of causation is doing, where we are intervening into the system. So now we are going into the system and changing a parameter. So let's say if we go into our robot assembly pipeline and we change something on it, and we want to see what would happen. So what if the load sensor was now set to 2000 instead of 1400? What would have happened in this case? The topmost rung of ladder of causation, which is the most interesting one, is the counterfactuals, where you are just imagining or retrospecting what would have happened if something would have gone wrong, or what if the load sensor was not faulty, would the anomaly still would have occurred. And we want to go to a future AI or AGI level models, we need a hybrid methods. So we would probably need rich symbolic knowledge, which can be used for reasoning tasks such as causality. So in the previous session, you already saw the use of neurosymbolic AI, where we can cooperate the deep learning models along with the knowledge graph capability to reason about our outputs that we have gotten. And one way we could do it is, we have on the graphical end, take the Bayesian network that we have along with the domain knowledge that we get from a particular domain. So you saw the knowledge graph that we had, you saw the process ontology that we developed, and create a hybrid model of causal neurosymbolic AI, a causal knowledge graph, which incorporates everything in this particular in any given domain. And this is, I'll spend a few minutes on the counterfactual scenarios and why it is even important to us. So we as human, majority of the times, have the causal notion of the world around us. And we tend to think about alternative scenarios which could have existed, for example. So maybe what if we had started 15 minutes early, because there was a mismatch between the program or the schedule on the app versus on the website. What would have happened? How many people would have joined? Maybe we would have ended up early, or we might have like 15 more minutes or 30 more minutes for the discussion sessions. So we are always thinking, or majority of the time, thinking about these hypothetical scenarios whenever we try to take any particular action. And I really like this poem by poet Robert Frost, The Path Not Taken, where I hope many of us have already have read this poem in our high school, where there's a traveler and he's going on a trail, he's hiking maybe, and he's encountered with 2 paths on his way, and he doesn't know which path to take. and he decides to take path A versus path B, but on his way, the entire time he's thinking, what if I had taken the path B? What would have happened? Maybe my journey would have been more comfortable. Maybe I might have encountered a waterfall, to be more scenic. But these are all counterfactuals scenario where what that traveler was actually thinking. But current AI systems or current AGI or agentic systems do not have the counterfactual understanding or the causal understanding of the world. So let's say we want to make sure these systems have those counterfactual abilities. What do we need? We would first require a causal structure of the domain or of the world that we want to deploy these agents in. And this becomes especially critical in safety critical domains. So very important in domains like autonomous driving, smart manufacturing, cybersecurity, and healthcare, where you definitely want to understand why does a given model or these deep learning models or neural networks are telling that you might have this particular disease versus the other. You do want to understand the reasoning behind the output that you get. To do so, we would obviously have to understand the causal dependencies among the components in the overall systems. And if we have the causal domain or the causal structure of the world, we would then effectively prepare ourselves for some counterfactual scenarios. So if something might have been different, how would the patient would have behaved, or how would our agents would have behaved, or how would the environment or let's say in the case of autonomous driving, these cars would have behaved. And to do so, we definitely need to learn the structure, which is a downstream task, which is a common causal discovery, which basically means learning the structure of the causal network and new causal relations from just the observation data that we have. And we are going to show you how we are able to achieve this in the next demo that you see. Now, how is causality and agents related in a way? I gave you a brief overview about we need causality in agents, but how do we incorporate it and how is it even related to agents? So there is this term called agency. And I like this recent tweet, or I don't know what you call it in X anymore, where Andres Karpathy, he says that agency is more important than intelligence. So what is agency? In individuals like us, agency basically means the ability of an individual to make meaningful choices and act upon them in ways that influence our life and our environment. And there are 4 key ingredients for agency. First is autonomy, that we are able to think autonomously. We can make our own decisions. Second, intentionality. We have the intention to do a certain action or to act upon those decisions. Third is capability. We have the capability to do something or to take the action. And fourth, which is the most important, is the sprinkle of responsibility. We are responsible for the actions that we take. So think about from an ethics point of view. Now, what is agency in agents? So that basically transforms to the ability of these agents to adapt the policy that they take based on how their decision would influence the environment. So think about it from a counterfactuals. So they would able to adapt if something would have changed in their environment, or think about it from the intervention perspective. How would, let's say, in our assembly pipeline, we identified, or the agent identified in the middle of the assembly pipeline, that the robots won't be able to assemble a toy rocket towards the very end. Now, what policies this agent that we would deploy could take where we would still get a final assembled rocket in the final outcome? We'll be talking about one of the most this important aspect, which is called as functional agency, which basically means it's a type of autonomy with respect to a specified goal. Now, what does that mean? It basically has 3 conditions to achieve a functional agency in any agentic framework. First is action generation, where the agent is capable of generating action based on information from the environment, directed based given any particular objective that they have to achieve. Second is the outcome model, where it is capable of representing relation between the action that it has generated to the outcome that it wants to achieve. Third is the adaptation, where how is it would adapt given a certain condition would have changed in the environment or in the domain where the agent is deployed. So talking about the action generation policies. So it requires the system to be able to specify what action to take for any particular objective to achieve. And there are three particular policies which can be considered. First is reactive, which basically means, let's think about a thermostat as an agent. So which it considers a reactive policies. So if a temperature goes above a certain threshold, activate the AC or activate the heater in the room. Second is the stateful policy or the stateful action generation, where you can think about the agents such as autonomous driving, where you have given a certain state of the vehicle, activate the take the steering from left to right, or activate the braking function or the braking action in the scenario. Third is the epistemic, which we as human incorporated. So we think about it from a context environment. So our actions are driven by the context we are in. It's necessarily that we would take the same action in every environment. It depends from the context or the environment we are in. The second one, which was the outcome model, which maps the actions to the outcome. They are basically goal directed behavior specifying actions that would achieve a specific outcome. And to do so, we requires a model of the word. Could we want to know if in this particular model, if I take an action, what would be the outcome? So if I take an action of changing the temperature of the thermostat here, how would it affect the temperature in this particular room? So I need to understand the functionality of, let's say, the AC, the flow, the fan, and so on. And this would differ from, let's say, if I want to activate or if I want to take an action to change the temperature of this entire convention center. And the outcome model follows the Pearl's hierarchy in a way. So it ranges from complexity. So the first we saw, the first rung of ladder of causation was the association. So it associates an action to the outcome. So that's a simple association, which are typically done on statistical correlation based. The second rung of ladder of causation was intervention, where we intervene and we saw what would be the outcome of an action that has been taken. The third was counterfactual, which basically imagines if I had taken a certain action, how would my outcome would have differed in this scenario or in any given scenario. The third most important functionality or condition for functional agency is adaptation. How well my agent is able to modify its behavior when a relation between an action and an outcome changes. If I don't have this adaptation, the system won't be able to maintain a goal directed. It would be stuck at a given point if I change something in my environment. So we definitely want effective adaptation so that it can reason or reflect about the underlying process that would lead to any given change that we have seen. Coming back to our SmartPilot, now how does our causal agent is used in SmartPilot for the case of root cause analysis? And Chaturangi is going to take it from here.
Yeah, so in earlier demo, we explained on how SmartPilot can be used in anomaly prediction, forecasting, and also like domain-specific question and answering. So in this demo, I'll mostly focus on the root cause analysis and causal discovery, which are the two main tasks that the causal lens agent will do. So this is the whole architecture that we have for all the four agents. And here you can see the causal agent is again connected to the InfoGuide Q&A chatbot, and it is doing root cause analysis and causal discovery on top of the time series data. Yeah, and yeah, so let's see how it is working. So let's upload the time series data. And since the session was ended earlier, we have to upload the data again here. So we upload a sample of the time series data that we have for the future factories, and it again gave us the dataset overview along with the data descriptive statistics of this dataset. And so these are the functionalities, these are the sample questions that we can try with the causal agent. So first the user can upload, user can select some of the variables among these whole set of variables that he want to use in the causal discovery process. So let's take like 8 variables relevant to the potentiometer and the load cell sensors of the 4 robots that we have. And user can save these features for causal discovery, and then he again can give some descriptive statistics of these variables. So this is a co-pilot system, so we want this to be more interactive with the user. So the user can add this select these variables, and then he can give the descriptions and the type of these variables. So here I'm giving the variable name and the type, if it is a sensor or an actuator, and the function of this particular sensor. And then he can save this as well, and then he can enter the causal discovery process, and then here it will run the causal discovery algorithm. So currently SmartPilot can do 2 causal discovery algorithms, lingam and define. So these are kind of like standard algorithms that we have. So for the demo purpose, I will show how it is working with the lingam causal discovery algorithm. So once the user select these variables and add the description, the system will give the causal graph associated. So this is the causal graph. So this shows the variables the user selected at the earlier stage. And so here this is pretty interactive, and it shows like if it's a sensor, it will print it in a blue color. And also when hovering on the nodes, you can see the function of the particular sensor, and also you can see the relation also along with that. And these node descriptions are not hard coded. These are the values, these are the node descriptions that the user gave at the earlier stage. And then this is a pretty user-friendly interface where the user can add more variables also, and then see how the initial causal graph will change accordingly. And so this is the canvas where the user can edit and like engage more interactively with the system. So here, when hovering on the nodes, you can see the type as the gripper potentiometer sensor. So all these type of these particular nodes we extracted from the knowledge graph. So it is grounded in the real world concepts and real world deployment setup that we have in the smart manufacturing knowledge graph. So it is pretty explainable. And then the user can download these causal graphs and study it and use them, reuse them for the later purposes also. And yeah, let's see how and what else that this causal copilot can do. So it can answer any question related to this causal graph, and also it can do causal reasoning upon it, and also we can do root cause analysis also. So let's see how we can do these things. And so hence this is a causal this is a copilot. The user is interacting with the user, and then so earlier we showed how it is used for animal prediction. So now user want to see what are the root causes of the particular anomaly. So that is why you need this causal lens agent. And then he can ask questions related to the causal graph which was produced, like is this particular sensor causes the other sensor variable and things like that. So it can involve with this CoPilot more interactively, and it is very good in answering any question related to this causal graph which was produced. And if we want to know what are the causal parents of these particular variables, so he can get an overall idea on what are the most reliable edges and what are the most like friendly edges with this particular sensors, and then it will give the strength also in between these two edges. So there is this amount of 2.0 edges, 2.0 connection between IRO1 gripper load and gripper potentiometer. So he can have an idea on, oh, this variable is more reliable and this is not effective in my animal prediction task, things like that. And yeah, so it is like so yeah, how much is the in numbers, how can you show the connection between IR of one and this variable, other variable? So it's like a numerical connection, the strength between the two two nodes. Right.
Which number then this relationship is trustworthy, or if it is under this number, then well, that might be a relationship, but we probably shouldn't trust that too much.
Yeah, so actually it also shows the true relationship. So if you in this causal graph, you see that there is a relation between IR for gripper potentiometer and IR for gripper load, but there is no direct connection between IR for gripper potentiometer and this other variable. So that strength gives the indirect relationship as well. So we are able to get that hidden pattern also through this causal graph. Yeah.
One more question, if you don't mind. Is there a way to quantify the relationship as well? Let's say, for example, this signal changed by 1%, then the resulting signal, like by which percent will change?
Yeah, of course. Like interventional queries, as with Karishini was suggesting, SmartPilot is able to do that as well. So I will show how that is happening. Yeah, so these are the questions he can answer on the causal graph structure which was developed. And then he can, like, let's see your question. Yeah, so I'm asking if R2 gripper potentiometer was 10.5, then what will be the effect on the other variable, things like that. So yeah, so it is saying that approximately 11.2 units will be the approximate change in the second variable that he's given. So it's, and then like some other questions related to causal reasoning. So this is type of a reasoning task that he can do. And then he can also answer these questions like what are the strongest what has the strongest causal effect on particular variable, and then it is giving the variable name including the strength of that. So in this particular, in the previous section, you see that it is a minus thing, so there is an inverse relation between these two variables. I will show you. So these questions does not have a relation with those parts. I will show. And so these are the questions he can ask. He can answer related to the reasoning part. And then let's see how it can answer the root cause analysis related questions. So you can go through the root cause analysis module using this particular function, And then so it takes some time to analyze the whole data set and run the root cause analysis and analyze the which variables has the most effect in the anomalies that were predicted earlier. And then once the root cause analysis is done, you see the results like this for each row. What are the root causes for the anomalous variables, if there is any? And then he can answer a range of questions related to root cause analysis, like what is the mostly root cause for this particular variable if there is an anomaly. And so he printed that most likely root cause is this particular variable with along with the strength. And then he can answer more advanced questions also, like uh, three most likely use causes of the anomalous variable, and also some reasoning questions also. So in this earlier question he gave the average strength also. And so here I'm asking if this particular variable is like a root cause of the anomalous variable of the second variable, and it is saying the answer along with the percentage of the cases exist in this particular data set that I'm using. And things like that. So it gives the answer in a couple of seconds. And yeah, so if it is not a strong root cause, then it is saying it is not a very strong root cause. It is a root cause, but not a strong variable to be considered as an action that you need to perform. And then let's see an example where he want to add another edge to this particular, another variable to this particular causal graph. So let's see, he want to add uh, the effect of this second temperature variable also. And then he can add this graphically through this particular section, and then the causal graph is updated with the new node, and whatever the question you ask later are based on the new causal graph which you have here. And then you can download this graph for further analysis that you can use later. And things like that. And also, so we know that it created the causal graph and it is good in reasoning, things like that. But we don't actually know if the causal graph that he produced is correct or wrong. So we need a method to evaluate. So how does SmartPilot do that? SmartPilot do that to, through two methods. So he can change the step. So we use something called stability score. So here we measure and we quantify how reliable our edges are. So we are using, like, so this is kind of a bootstrapping method that we use. Means internally we run this causal discovery algorithm like multiple times, like 20 times, and pick the most stable edges and give the finalized graph to the user. So you can change the stability score by changing this particular vast, as Ranjit was asking. And then he gives the information with the mean strength of these edges and the standard deviation and calculates the stability score. So we have our own mathematical equations that we have developed for this particular bootstrapping method. So if you're interested, we can share with you also. So here it identified only two stable edges depending on the parameters he selected to the stability score and the minimum causal strength. and then the updated causal graph is displayed, and here you can see the stability score also, and it is also pretty interactive. And then he can save this also and use for further analysis. And also the causal graph is updated in this canvas also. And the second method is that we can do like counterfactual and causal effect analysis method. So as Utkarshini was also explaining in her slides, we can change one variable in the observational data, means the original time series data we input, and then see how it affects some other variable, and see if the same information, if the same results will be propagated through our causal graph also. If it is so, then our causal graph is reliable and accurate. So let's check how it is working. So I am setting here IRO1 with the potentiometer and IRO4 gripper load. Let's set this value as something like and then he can set, if he can change the range also, like check between 50 values up and down in this particular range, and then it will check with the observational data and see if the same causal relation is can be seen in the observational data and also the causal graph also, and it is giving a very good explanation of if the observations are different and what is the reason of things like that. And uh, you get the distribution of the particular variable also, so you have an idea on what values to change. So initially, if the user does not have any idea on the range of the particular ranges, so it can get the ranges from this value distribution graph. Yeah, this is how, and also, so here we did it for only one variable, and we can evaluate all the variables in this particular causal graph and then see how it is changing. So here it gave only two relations as stable based on the parameters I set, and then it is giving the effect and the error also, and it is kind of interactive and visually appealing, because here it marks the correct edges in green color, and so pretty cool. And you get the heat map distribution also, and it is very explainable, and it is given reasons why you are saying this is a true causal edge or not. So yeah, that is the causal lens demo. And in the next section, Corey will be explaining on the real world applications. So let's continue. Okay. You'll have to now maneuver here. Is that what?
Just, okay.
Yeah.
This one? Yeah. So you can't see it here?
Oh, I think we can do that.
Hmm?
I mean, you want it here. Okay.
It doesn't matter, actually.
Mm.
Okay, so I'll spend a few minutes talking about just applications of this technology that my colleagues been working on talking about. Specifically, we divided, or the two topics I'll focus on mostly is the application domain, just talking about production lines and manufacturing, and then some of the CoPilot tasks that we would want to see and use within these domain applications. So like things like causal modeling and root cause analysis. Yeah. But just to start out, like, you know, the AI market in manufacturing is quite large. Like, it's projected to be about 800 billion in 2025. So this is actually the largest market, at least according to some estimates, bigger than communications, natural resources, consumer goods. Everything else kind of falls way behind. So, it's quite a big market and actually growing. The amount of data that's being generated by these manufacturing lines is quite staggering. I mean, the next highest domain is like maybe half as much, right? So it's a big market. There's a lot of money involved, and it's generating a lot of data. So this is really like fertile ground for disruption by AI, especially the agentic AI that my colleagues are working on. So if you're interested in the topic, this is quite a good one, I think. But the issue is that these production facilities are very large and complex, and they're kind of set in their ways. So actually getting them to actually use new technologies is quite difficult. But it's also the reality that the demands within these manufacturing lines are shifting constantly. So when COVID happened, a lot of these manufacturing lines actually shut down because people stopped buying stuff, right? So there was nothing to produce. But that's not exactly true. People started buying different things, right? So they stopped buying cars, but they bought a lot of test kits and face masks. So what ended up happening is a lot of these production lines had to shift from what they were producing before to something new. This is actually a very difficult problem. This is actually happening more and more, right? So basically the expectation now is that a manufacturing line should be able to change and to be able to develop a new product actually quite rapidly. Yeah. So when we think about products, a lot of design goes into actually engineering a product, but a lot actually also goes into the processes for actually constructing that product, right? So this is the production line. And as far as some of the pain points that we come across, right? Of course, we want to reduce the cost of producing any product. This gives us more revenue, more money. We need to reduce the time to market to get it there faster. These lines are so complex that the knowledge of the line has to be split among multiple people because no single person can understand all of it, right? It's simply too convoluted and complex. It just can't happen. But it's also true that the number of experts who actually understand these lines is getting smaller. So people aren't learning this anymore. Yeah. So it's kind of it's getting bigger and bigger in some ways. But the number of people who actually understand them is decreasing. So it's kind of a strange situation we're in. But for this talk, what I'm particularly interested in is the point between the start of development over here on this side, basically after the product's been designed, to the start of production. And this is where we can kind of really ramp up and start producing things for mass market. And we want to actually get from the start of development to the start of production as quickly as possible, right? And we want to lower what's called the internal defect cost. So this is basically malfunctions happen, this costs us money. We want to lower that as much as possible. And that requires us to find and fix any issues within this, what we call the ramp up phase, right? Between the development and the production. That's kind of what I just said here, right? So there's this period where we start producing just small samples of products. And then during this phase, we try to optimize the process as much as possible, work out any of the kinks. And then once this occurs, then we can actually go into full scale production. All right, so we want to do this as quickly as we possibly can. And the way we actually implement this is through what is kind of an optimization loop, right? So we want to find and fix these issues before production begins. And we have these 3 primary stages or steps that we do, right? So the first was just detecting anomalies, malfunctions, these kind of things. Chatharangi actually talked a bit about how this occurs, so I won't go into that. But that's kind of only the beginning for us, at least. So once you kind of detect an anomaly or malfunction, some failure within the production line, you want to know why it occurred. Yeah. And the reason why you want to know why it occurred is so that you could fix it so it doesn't happen again. And this is the process optimization part. And then once we fix it, we intervene in the system, change some parameters, then hopefully that anomaly doesn't occur again. But we cycle through this process many, many times as fast as we can until we get to the point where the anomalies or malfunctions stop happening and the cost that we attribute to these malfunctions actually decreases to a suitable level, right? And then we can start production in reality. Okay, so product quality estimation. This is kind of how we implement the anomaly detection. So what we do is within a particular production line, we need to check the quality of the product, right? So this happens at the end, of course, right? So we won't sell it if it's a malfunction or it's faulty in some way. But actually throughout the production line, we have stages where the product is actually checked to see if something is happening. And the reason we do this is because we want to be able to find those anomalies or malfunctions as quickly as we can to get them out of there. We don't want to waste resources actually building something that's never actually going to go to market, right? So this is actually called the scrap rate. So how much of the product we actually have to throw away before we can actually sell it. And we want to get that to as low as possible, right? So so I'm working with some groups that are looking for like 50 parts per million, right? So it's a pretty small number, but we still want to get it lower, you know. So here's a bit of a schematic of a production line, a very small one. So there's 4 stations here, and then at the end of the 4 stations is this quality check, right? So this is the point where we inspect the product to see if there's some failure. If it's okay. I mean, here it says if it's going, it goes to product. In reality, there is not 4 stations, there's hundreds of stations. This just means it can go to the next phase. And if it fails the quality check, then it goes to scrap. Yeah. And then at the bottom, we have observed parameters. So these are values or variables within the system that we can observe, often through sensing or other techniques. Things like, in this case, force or pressure, right? And it's from these values that we can actually determine whether the sensor or the product is faulty or not, right? Okay, so once we've determined whether there's some malfunction, we want to determine why it malfunctioned. This is the root cause analysis process. And we don't want to actually know just what caused the failure, because these malfunctions or failures are never just one-offs. Typically what happens is something happened, 3 stations back, and then the problem cascaded, right, until finally it failed this quality check. So what we want is actually what's called a failure path. So we want to know the first time the anomaly occurred, and then every subsequent time that a malfunction occurred because of that original anomaly, right? So this is what we call the failure path. And this is what we're really after. So here's another schematic of like the same kind of toy production line. And what we're seeing here is a causal graph superimposed over that production line, right? So each variable here is a parameter, and we can see the failure path from the failed quality check all the way to the root cause. Now, you might, at the other end, we see kind of the observed and unobserved parameters. So the observed ones are actually ones that we have sensor values kind of measuring, something we can actually write down in the data sets that they upload here. If we're only looking at that kind of data, you would see, okay, the root cause is within station 2, and it's a function, F1 here. Because the variables that are dashed are actually unobserved. And this is actually really problematic in real production systems. So it's estimated that almost half of all parameters or variables in the systems are actually unobserved. So these we don't actually measure, but they have causal effect. So in this case, the true causal, the true root cause is like the stiffness of the material, which caused too much force to be applied, right? But we don't actually ever write down or measure the stiffness. Yeah. Okay, so now that we know the root cause, we want to use that information to then optimize the process, right? And this is typically done through interventions. So you would go in, you would change some configuration, right? You would move one station, you would replace something, and then hopefully that would solve the problem. But in reality, this is actually very expensive. Like you can't just shut down a manufacturing process. It'll cost you millions of dollars per minute that it's shut down or something like that, right? So this actually doesn't happen in reality. So what we want to do is actually be able to simulate changes to the production line, and then be able to show that these interventions do, produce better outcomes, so less scrap rate, things like that. And we do this using the counterfactual analysis that Darshan talked about, right? So basically in our simulations, we could change some characteristic or some parameter and then run simulations to show that if we did change that thing, then we would have better outcomes in the future. Yeah. And then if we're confident enough in those, then we can finally go in and actually change it. Okay, so it's nice to think about these techniques. What happens in current systems is that a lot of this root cause analysis, process optimization is done by the factory workers on the floor or engineers. And what they do is simply think through the problem, right? So there's various techniques for this. There's something called 5 whys, where someone will simply think to themselves why something occurred 5 times. Well, 5 is kind of arbitrary, but I guess it could be 10, but it's simply just keep thinking through the problem to get deeper and deeper to find out where the true root cause is. FMEA is the functional mode effect analysis. It's a way of doing risk assessment. Pareto analysis, if anybody knows the 80-20 rule, it's basically just an application of that. It's an acknowledgement that 80% of the problems come from 20% of the root of the causes. And so understanding what those 20% of root causes is quite important. And then fault tree analysis is a way to diagram your failure paths through the system in kind of a systematic way, right? So the issue is like, these are all great, but they're simply ways of helping people, engineers, think through the problem and solve them. And the success of this really depends on how good the engineer is, right? So they're very susceptible to failure, and they take a long time. You'll spend weeks or months doing this, and it may not produce any kind of good result, right? And so we really kind of need something like this product that Chaturanga and team are developing. So this causal lens, causal agents, which can kind of take over some of these tasks that are kind of cumbersome for people to do. And so at the heart of this causal AI agent is the causal graph model, which is kind of just, this is the brains of the operation. So this is the model that understands all the causal relations between the variables within the production line, and also understands all the domain knowledge. Yeah. So in this diagram, the production, that's kind of the observational data, the observed parameters that we can get from sensors. The development data would be things like this, like any kind of information that the engineers can actually bring to the table and tell us about the system. It's quite useful. Domain knowledge. This is related to the knowledge, the process knowledge and manufacturing knowledge that Chaturanga is developing within the knowledge graphs. And then based on this causal graph model, we can do the root cause analysis and process optimizations. Yeah. So just a quick example is the integrated power brake. So basically, if anybody has a vehicle that can detect objects in the road and will stop automatically, basically this is a system that does that, right? In this case, I mean, we're not going to talk about the entire product, but in this case, there's a motor. That motor needs to be fit into a housing and then needs to be fastened with a few screws, right? And so basically, we start with just the components of the system, right? So we have ring gear, end shield. Basically, they're just, you know, the components here. But we put these into our graph. We then take the observable parameters, right? Within the production line, things like force or pressure or torque, velocity of the screw as it's being screwed in. We add this information to our graph, also including the quality checks, of course. And the most important thing is that we want to kind of derive the causal relations between these parameters. And this comes about through the causal discovery processes that the questioning talks about. And this is typically learned from the kind of observational data that we get off the line. But we don't just end with we don't just want to know the causal relations. We don't just want to know the relation between the parameters. Going to your question, we want to understand the mathematics behind it, the physics behind those causal equations or causal relations. And so for each variable, we actually learn a structured equation. These are structured equation models. And they follow the Markov assumption, which basically means that the value of any given variable, it can be fully derived from just its parents, right? Yeah, so, and actually it's these equations that allow us to do the counterfactual analysis, the interventions, run our simulations. Yeah. And then finally, we take the domain knowledge that's actually relevant for this particular product and the line that's being derived to develop this product, right? So any information about the stations, the lines, the machinery, the sensors, as well as the products that are being developed. We integrate all this domain knowledge and process knowledge into the graph as well. And so all of this comes together. This is what we refer to as the causal graph model. And it can be represented as a knowledge graph as well. So yeah, that's what allows us to actually integrate all of this knowledge together. I don't think it was mentioned by anybody so far in this talk, but we also have a causal ontology and causal graph to represent the causal relations between the variables as well. Yeah, and so yeah, once we have these graphs, then we can kind of do the root cause analysis. We can run the algorithms over our causal graph to do the root cause analysis, and as well as the simulations with counterfactuals analysis. Yeah, so basically in the simulation, what we'll do is we will change the parameters and then see the downstream effect, and we want to find combinations of parameters that lead to good outcomes, basically quality checks that pass rather than fail more often. Okay, so we really need to use some of these advanced causal analytics techniques to improve the production lines. But we have a couple challenges. One is that there are a lot of methods for causal discovery, causal reasoning, root cause analysis. They're not just one method. There's hundreds of methods. And it's not quite clear always which to use in any given situation, right? And as I said before, the people doing this are factories, or they're just workers on the factory floor, they're engineers. They're not causal experts. there are causal experts like Carson here, but like they're not working on the factory, right? So we have this kind of skill gap problem. So we need systems like the CoPilot here to actually allow people who are actually working in the factory to access and take advantage of all of this cool causal analysis technologies being developed. Yeah. Yeah, and that's the purpose of the causal CoPilot. We think it'll really kind of help move manufacturing forward. But the reality is actually, we can talk about this, but actually deploying it comes with all kinds of problems in reality. So I'll let Fadi tell you all about that.
So we're going to take a bit of a step back here. We've talked a lot about what the CoPilot is, what it does, and how great it is to have it on a manufacturing shop floor. But of course, with any new innovation and any new product, there's going to be a lot of different challenges that you have to face when you start actually working with it, and when you're actually trying to develop it. And specifically in this case, there are a lot of different challenges that we have to look at. And in this little section we're going to talk about, we're not only going to be talking about specific agents or a co-pilot or whatever. We're going to talk about as AI in general, on what kind of issues what kind of issues we can run into when we're trying to incorporate AI with manufacturing systems in general. In order to kind of help us organize these train of thoughts, I kind of came up with these 3 different layers that we need to think about whenever we're trying to think, all right, how can I incorporate a new AI system into my manufacturing shop floor? At the bottommost layer, we start talking about the component level. That's when we are actually creating our AI model, for example. We have a specific use case that we want to utilize AI for, and we start to think, okay, this is the part of our manufacturing system that we're going to utilize it in, and this is the equipment that we need for it. And then at a higher level, we start going into the system level, and that's when we think about, if we have multiple different models and multiple different use cases, how do we incorporate those together? In our example here in CoPilot, our system is the whole CoPilot, where we have our causal lens, our info guide, our PredictX agent. And then finally, there's the actual operational level. What kind of challenges might occur when you're trying to, you actually want to deploy AI onto manufacturing systems? And here we start talking about more of the hesitations with AI within manufacturing. But let's start out from the bottom and work our way up there, shall we? And the component level, there's 2 different kind of sides that I need to think about. There is the model side, and then there's the mechanical side. Here I call them mechanical aspects and model aspects. For the model aspects, we'll talk. The first thing we need to think about is data. And data really is one of the most difficult things to acquire when you're working in manufacturing shop floors. You want to create an AI model? Well, good luck, because you're going to need all the data that you can get. And in real life manufacturing facilities, a lot of companies are very hesitant to release their data, and they're also hesitant to create data sets that are available for the public, which makes sense, due to proprietary reasons, or for issues that they don't want to, release any of the information from their own systems. And so here's you to think about how much data is actually needed for your specific use case. Do I need 30 hours of data? Do I need just 5 minutes? And one of the things that also you need to keep in mind when tackling this issue is that data can be expensive as well. If I want to create a use case where I want to be able to classify, well, I have this anomalous, I want to classify an anomaly in this specific time frame, well, am I going to run my system to create an anomaly? If we're going to make that if we're going to actually have to do that in a real shop floor, that's going to cost a lot of money for the manufacturing system, for the actual manufacturer. They're going to have to stop their production line, simulate this anomaly. Of course, this also ties in back with the idea of creating synthetic data with anomalies, which is a topic that my colleagues have also talked about in this presentation. Another issue is, how do you synchronize multiple data generation systems? If I have 2 different manufacturing systems that are running on different controllers, one has a specific time stamp, and the other one has another, or one has one frequency and the other has another frequency. How do you align these two data sets so you can have one uniform one that you can actually use to train your model? And then finally, how do you actually structure this data? What's the best possible or what's the easiest possible structure to put or to integrate all this data together? Here, for example, I do have a little screenshot of the two different structures that we have for a data set, which is for the feature factors data set that we talked about earlier. One structure is a bunch of CSV files, whereas the other is a bunch of JSON documents and images. So those are two different structures that when you actually want to utilize this data, you're going to require different data processing techniques to be able to access them. And then the next the next phase is actual feature selection. Well, when you want to train your AI model, then I need to think about how many different classes are there if I'm trying to classify a specific anomaly. Do I have 2 anomalies, 3 or 4? And when you start to increase these classes, you're going to run into more complex issues as well. You're going to need more data, and this also ties back into the data acquisition phase. How can I minimize these numbers of features just for the sake of actually having simplifying my use case? Do I need to install new sensors into my system to be able to uncover some of the features that weren't there before? If I'm trying to find, for example, a specific crack in my final product, am I going to have to install now a camera to be able to see it? I'm getting a new camera and putting it into my manufacturing system. That's a whole new process as well. It's going to take a lot of time, and so that's another hurdle that you need to think about when you're trying to utilize AI at this specific level. In the third phase, this is the algorithm analysis. Well, say you're able to acquire the data that you need. You've selected all the features. Everything is perfect so far. Now let's actually train our models. After I train my models, I turn out, well, a lot of the different state-of-the-art models that I've tried to utilize, maybe some of them give me a 98% accuracy, whereas others give me 87% accuracy. Well, obviously a 98% accuracy would be perfect. Wow, if I want to put that would be the best choice, right? Well, you never know, because maybe the model that gives you the 98% accuracy requires so much computational power that it's almost inefficient to put it in your manufacturing system, or even impossible. So you have to end up with the 87% accurate one. But now, is 87% enough for that specific use case, or do you need something that's even better? These are all the little considerations that need to be handled when you're trying to look at, when you're trying to deploy the specific model. And it really depends on your own manufacturing system. It depends on your use case. It depends on how much funding the specific project has. So there are these different aspects that need to be thought about. And then finally, the actual model deployment. So this kind of ties all these 3 sections together. Once I have my model, I have a good little accuracy rate. It's an efficient model. Well, now think about the specific use case. Do I need my model to predict something in near real time? How much latency can I afford before I can get a prediction out of it? If it's 3 seconds, if it takes 3 seconds for my model to give me a prediction, is that going to be too late? Are my robots going to crash if it does that? Who knows? That's something to also be aware of. How can you also, if your model needs these data from different systems, going back to the data acquisition issue, if when you have different systems and you need to actually integrate the data together, now you want to deploy it, how do you actually make sure that the data coming from these different systems are integrated together in real time and in sufficient time for your actual model to give you actionable insight? And do I need to integrate more hardware? Like I said, if I want to use the 97% accurate model that requires so much processing power, how do I need to buy a new industrial edge device, for example, to deploy it on? Do I actually need to get it? Do I need to deploy it on a server? Do I need to buy a server? And then if I deploy it on the server, how much lag is that going to add to it? So these are issues that kind of compound, but there's always going to be a balance that needs to be found when trying to reach the certain efficiency and the certain use case that you're trying to achieve. And switching over to the mechanical aspects. Remember, there was the model aspects and now mechanical. Sensors, they can be your best friends or they can be your worst nightmare. They can either give you great data and they can make your life so much easier and you can get so much different insights from your system, or they can give you so much of a headache that you end up just ditching the whole project. There are some issues that you can run into when you come into sensors. Some of them, the first issue that always pops up is the idea of accuracy. A lot of sensors tend to produce a lot of noise, and noise can also be detrimental for your model's accuracy and its actual predictions. So there's a lot of different there are filters that you can apply to minimize noise. However, at some point, utilizing a sensor over and over again for years on end, noise keeps increasing, and so that requires also upkeep. And that ties into the idea of data drift. If a sensor is being used years on end with no maintenance, the data that might be coming out of a sensor ends up being null because it no longer resembles the data that you trained your model on. And the idea of calibration. This sensor might work in one environment, but not in another. So these are issues that sensors usually come up with, that you can usually struggle with when using sensors. Also, availability of them. Do I need more sensors in the system? Tying it back to the model aspects as well. Labeling. If I have a big data set that uses both images and that uses analog data, labeling that huge data set might be a lot of time consuming. And if that specific use case that we're trying to aim for needs to be deployed as soon as possible, well, you're going to need a big team to be able to label all of that data. And then normalization. Sensors, like I said, do have varying accuracy. They have different resolutions and different output formats. So how do you make? So you also need to think about how you can convert and converge and integrate all these different types of sensor and outputs to one unified data set that can be used in real time even. Apart from sensors, the manufacturing systems themselves, especially these days still in factories, there's a lot of facilities are still hesitant to integrate new equipment and new technologies into their production lines, because if it ain't broke, then why fix it? Because that's how they think. However, a lot of manufacturing systems, right, in present day are still do utilize a lot of legacy systems, and they are all kind of siloed into different into different hemispheres almost, where you can't really integrate the data that's coming in one system to another without having to introduce a new hardware. So these legacy systems that all use proprietary data, then you need to think about, if you need the data from both of these systems for your specific use case, you're going to have to think about how you need to integrate both of these together. How do you handle these complex systems, and how can you add the ability to convert and integrate the systems together? And now moving on to the second level, which is the system level. Essentially, this is the idea of, this is where we start thinking about maybe systems engineering. If I have if I have two different agents or three different agents, which agents needs to act first before the other? Is there a specific data pipeline that I need to adhere by so that my whole CoPilot, for example, can operate correctly? Do I need to first have a specific prediction, and then this prediction goes to my causal lens? And if so, is that data propagation going to happen in time so that the technician can then view the insights required in the proper time frame? So this is the idea of just how do things fit in with each other, what needs an input, what does each output go to, and of course all this is going to require a whole unified system together to be able to come up with this I guess pipeline. And then finally, there is the operation level. This is here where we start talking about theoretical hesitation about using AI within actual manufacturing. And from just to be able to kind of dumb it down a bit, we've kind of been able to figure out 4 specific categories that describe manufacturers' hesitation to include these new technologies in their facilities. First one is security. The idea of using AI is kind of scary in manufacturing systems. Systems they do utilize a lot of big machinery. It can be dangerous. They're using a lot of force, a lot of pressure, high heat. If I have an AI model that is delegating jobs and enforcing different parameters on these systems, are my technicians and factory workers still working in a safe environment? If I utilize technology like a CoPilot, is the excessive agency something that's scary? How can I allow it? Can I allow it to create decisions on my system? Of course, including a human in the loop and the whole idea does help. And then the idea of also prompt injections. Can a malicious actor get some information that they're not supposed to get their hand on from by using these copilots? Latency issues. We've also already talked a bit about this in this section, but the idea, if we have real-time applications, stuff like collision detection or anomaly detection, can my copilot come up with these insights quickly enough for a technician or factory worker to be able to halt the process without having any big problems happening? Because if two robots collide and then now you have two pieces of equipment that costs thousands and thousands of dollars malfunctioning, well, your facility is going to go into some debt to be able to fix that, and we have a lot of downtime as well to have to fix it. And if we scale up our models, our systems, our softwares, scale them up to include more capabilities, more agents into our copilot, is the increase of this data pipeline is only going to increase the latency as well. How do we handle issues such as those? Trustworthiness. Again, ties back into the whole idea of, can I really trust my AI system to handle my shop floor equipment? Is it reliable? Is it going to come out with the correct output each time? Is it robust? If a new issue pops up to my AI model, is it going to be able to come up with an actionable decision on this new event in a robust manner rather than just on what it's trained on? Is it safe? Is this new decision or new change that it's made to my system, is it safe for my factory workers? And of course, explainability is very important when it comes to using AI in manufacturing, because transparency and transparency and explainability are very important to make sure that there are no decisions that aren't unaccounted for. Someone's always going to have to take the blame if something goes wrong, and you cannot just say, "Oh, the computer did it." And fairness. If I ask my AI, for example, to allocate my resources for a specific job, is it gonna allocate it correctly in a fair manner? Is it gonna ask robot 1 to do so much of the 80% of the job and robot 2 only 20% of it, or is it gonna ask both of them to do 50% of it? These are when a human comes up with, for example, with these job distributions, there are different load balancing acts that they think about before coming out with it. Is my AI system going to do the same thing? And then finally, cost, and that really is a big factor as well. Well, specifically in this specific slide, we talked about LLMs, for example, or copilots. The larger the prompt length, the more it's going to cost. The larger the request volumes, the more it's going to cost. And the more you want to scale your use case, the more it's going to cost. So it's just one thing after another, and that's another thing why a lot of manufacturers still are still a bit hesitant on using this kind of technology, because there hasn't really been a precedent yet. There's no ideal standard to think, oh, this is how much budget allocation I need to make sure that I'm going to have this return on my investment. And of course, there's also a lot of hidden costs when it comes to utilizing this sort of technology. There's downtime for development and integration. This was kind of talked a bit about by my colleague story about how we go from start of production from start of development to start of production, right? We do as the development time. That's going to cost a lot of resources. It's going to cost research money, salaries, monitoring and maintenance to make sure that my model still works correctly. Data prep and cleaning, that also adds up. So these are all some I think very reasonable reasons that a lot of factories still do have these hesitations, but hopefully with time, a lot of these challenges do end up getting handled, and we can start to see a lot more of AI systems in manufacturing. And that would be the end of my section. Do you want to take the rest of this?
Yeah, so we acknowledge our grant. So we are funded by this RI to enabling factory networking, and also we acknowledge our professors, Professor Amit Chet, Professor Rami Harik, and so these professors are from AI Institute and Clemson Competence Center, and also we acknowledge Dr. Abhik Banerjee from Swinburne University, who helped us in getting the data sets and like domain specific expertise also. Yeah. If you have any questions, we can answer, and thank you for attending the tutorial.